general relativity, step by step. We've developed this Riemann-Christoffel curvature tensor here, which is quite a beast. Oh look, it says 3, 1 there, and it should be 1, 3, of course, because it's got 1 upstairs and 3 downstairs indices. I think now is a good time to well, just point out that there are, well, as I've said, there are different conventions. People put the indices in different ways, different places and different orders and different signs as well. But there's another thing which you'll see in the literature. I've just casually written IJKL for the Riemann-Christoffel symbol, but you see different conventions. Sometimes you see I and then a space JKL. And so they're in these guys are in some kind of order. There's a kind of missing space here where the first downstairs index would go. Now I've not been making a distinction about that. I've been talking about this using this. Well, it's not a shorthand notation. It's just that I don't really see a justification for having this rather complicated structure here. So you see complicated tensors like this. It might have IJ up there, and then K, and then an L, M, N, O, P, all in a particular order, whereas I would write, or I have been writing in this course, T, I, J, L, M, and then K, N, O, P. I guess it boils down to whether there's a difference between a tensor I and then J versus T, J, and then I. You can see they're in a different order. I've not been making use of that distinction, but I want you to be aware that that's a possibility. Yeah, maybe I'll use it later in the course, but for the moment I'm just going to leave that. Just use an upstairs and a downstairs index without regard to their position. If I talk about the tensor I, J, K, L, let's say, and I want to express that in barred coordinates, what I've been doing is I've been going di-x, 1, 2, 3, and then di-x. And then we've got the primed coordinate system here. Oh, that's the primed coordinate system. Here's the unprimed. I'm going to run out of letters. I, J, K, L, M, N, O, P. Let's just see if I can do this. We'll do the I first. So that I is barred, so it matches that. That M is summed with this M here that's not barred, and then the J, these are bar, J, bar, K, bar, L, which is summed with the N, O, P. So that's the rule for equals that. So that's the rule for transforming it. And of course, notice I'm making extremely heavy extremely heavy use of the Einstein summation convention. Because otherwise I'd be writing summation conventions, I'd be writing summation signs, and I'd be here forever. I just want to point out there's another, it's not a convention as such, but sometimes you'll see, if I've got a tensor Tij, then sometimes you'll see the transformation written like this. You'll see it written as equals T, and then the barred coordinate system. The bar is indicated on the superscripts and the subscripts. Now let me just do that. Sometimes you'll see dashes as well. J bar, and then that's I and J. See if I can get this right. Di-x, 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 and then that I bar is this. Oh no, look, I need... Oh, I was going to say that I'm confusing my I's and my I bars, but it doesn't matter because I bar is a different symbol from I bar. So this one here is d for dx bar of I bar. That I is summed with that I which is in the unbarred system. That j is summed with this j, and that j bar is that j bar there. So you're using the index to indicate transformation. Which is great, except that I don't quite like the way that I've got I, which is already difficult to see, and then a bar on top of the I. Sometimes you'll see TI dash, but then you've got a dash on a superscript. On a superscript, I just think it's difficult to see, and it's difficult to typeset. But the one advantage, well, I say advantage, the one feature which you've got is that you can transform the elements one at a time. So here, you'll notice I've gone from ij to I bar j bar, but I can just pick one to transform and leave the j alone. So there's my tensor t, it's looking a bit messy. There's my tensor t equals t, and I'm just going to transform one of those. So that's di x by di x. That's summed, and that's a bar, and that's a bar there. Actually, and I've written it, I can just do that. So what I'm doing here is I'm just transforming one of the indices from the frame, from the regular frame to the barred frame. Now, is that an advantage or not? Well, it is, because you don't need, what you're saying here is that you don't need to transform the whole thing. You can just transform the tensor index by index. Yeah, but that's not really very useful. Certainly not at the level I'm presenting relativity in this course. So I'm not going to use that. I'm going to transform the whole stupid thing. So I'm going to say I'm going to say t bar ij equals t ij k l di x. It's a good thing to do this, just to go through. That k is summed with this k here. You'll see I can just write the order of these guys in a different, I can just swap the order of these two guys over, which means that this notation here, excuse me, this notation, where is it? This notation here, where you preserve the order of your indices, is not necessary, simply because I can commute my my partial differentials past one another. Let me fill in that L sums with that L there, that I is that I, that's in the barred frame, so that's a bar, that J is that J there, so that's barred. And of course this is all summed over L and K. So it's a nice linear transformation. So that's how I'm going to do it, and I'm not going to use this. Stop.